Here we are in Unit 10, Lecture 2, where we're going to take and expand upon that water that went into the atmosphere back in Lecture 1 and part of the water cycle, and that causes the humidity when there is a lot of water in the atmosphere, and see what happens to it as it starts to leave the atmosphere. And one of the things that happens is clouds form. And so this is all about the formation of clouds, cloud formation. Lecture 3 will be about the types of clouds, and Lecture 4 will be about precipitation and fog. But back to Lecture 2, what this is, on cloud formation. Well, for a cloud to form, we need to know what a cloud is. Or before we can talk about how a cloud forms, let's talk about what it is. And a cloud is a collection of small water droplets or ice crystals. So technically a cloud is either a solid or a liquid. If it's ice crystal, solid. If it's water droplets, it's liquid. And they are suspended up in the air and floating in the air. And they form as the air gets cooled. And as the air cools down, water vapor condenses into either liquid water or it desublimates, the opposite of sublimation, which is actually called deposition, deposits into ice crystals. And whatever temperature this happens at is called the dew point. And that dew point, you'll probably see in your notes at least, spaces where you'll just see the letters capital D, capital B together. Capital D to capital P is dew point. Anyway, so in order for water to vapor to condense and form a cloud, water vapor will condense all on its own. But in order for it to form a cloud, there needs to be some kind of solid surface for these water droplets or ice crystals to form around. Alright, now the troposphere, which is where we live, doesn't contain large solids, but it contains billions of small solid particles. Alright, like dust or pollen. Alright, these tiny solid particles that float around the air. So as that happens, the water condenses around this dust or this pollen. We'll talk about that a little more as we keep going on. And then the last thing that is needed to happen is we need the rate of evaporation must start in equilibrium with the rate of condensation. So we have to start at the dew point. Alright, this whole part here about rate of evaporation in equilibrium with the rate of condensation, that leads us back to dew point. That little tiny solid particle I was talking about that the water has to form around is called a condensation nucleus. So it's at the center of the condensation. It's a solid particle where the water vapor condenses on the surface of. Alright, let's say we had a little tiny salt crystal hanging around in the air. Here's the salt crystal, these green and purple little dots here in this little yellow cube. That's floating around up in the atmosphere for some reason. The water will come around and intermix with it and disperse in it, little droplets of water, and you end up with this whole big water drop right here. Alright, and what you can see here, down here at the bottom, and I believe you have this picture in your notes with the words, but if they're hard to read, rewrite them. Alright, kind of explaining what happens. The water is attracted to the negative and positive ions of the salt crystal, and so we get this water droplet that has a lot of molecules of water, alright, intermixed among the different molecules of that salt crystal. And without that salt crystal there, the water molecules would just be kind of floating around in space, like the left-hand picture. Here it gathers them in a clump, and that forms a little tiny water droplet. So that's the main way clouds form, is the water condenses or crystallizes around these solid particles. To kind of simplify the process more, to look in a little more deep in the process besides the condensation nucleus, so the sun, right here, sends electromagnetic radiation, electromagnetic waves to the Earth's surface, which heats up the Earth's surface, most of which is covered in water, heats up the water, and the warm air rises and expands. Alright? As it expands, alright, it rises. This causes the atmospheric pressure to decrease. As the air molecules are expanding, they're getting farther away from each other, so there's less molecules to push in an area. Causes the atmospheric pressure to decrease, which in turn causes temperature to decrease. So the air warms, which causes atmospheric pressure to decrease. This atmospheric pressure decreasing causes the temperature to decrease. We have a special name for that. It's called adiabatic cooling. All right, and it's part of a cooling process. Like if you've ever been to really hot places or some fancy places that cool with mist, kind of think in the same way. But adiabatic cooling, the big thing is air warms and rises, causing the atmospheric pressure to decrease, which eventually causes temperature to decrease, and this is called the adiabatic cooling. When the weather is clear, it impacts how quickly that rising air cools. So when we have clear weather, we have the sun having its rays hit the earth more. There's more rays hitting the earth because there's nothing stopping it. So the air, again, warms and expands, and rises, expand, and the temperature decreases about 1 degree Celsius every 100 meters. Alright? It's called the adiabatic lapse rate. That's just how fast the air cools. Alright? Or how high up air needs to go to cool a degree. So on clear days, the temperature decreases about 1 degree Celsius for every 100 meters the air rises. On a cloudy day, alright, some of that heat gets trapped by the clouds. So the temperature decreases, only goes down about half a degree to just under a degree per 100 meters. Depends how cloudy it is. And the big reason for this, the slower rate of cooling, is from the release of latent heat. As the water condenses, it releases energy. If you think back to that graph that we saw the other day, if we had water, alright, temperature increased, then it boiled, and then we had gas. And this right here is where it boils. Alright? And where that water is boiling, when that water's boiling, we store energy. Alright, so water boils, energy gets stored as it goes to a gas. Well, going the other way, if we start with our gas, and we let our gas cool, it will then condense to form water. Alright, if its arrow's going that way, here it was going up. And so here is where we have condensation, which is the opposite of boiling, or evaporation. And since boiling stores energy, condensing releases energy. And that energy that's stored or is released is that hidden energy called latent heat. And so that latent heat, if you think about it, a little bit of heat is released as the gas condenses to liquid, forming the clouds, that kind of heats the air up a little bit more, so it keeps the temperature from decreasing as fast. The condensation level takes a look at how high up in the air the clouds form. And this is all based on the dew point. Alright, if you have a DP in your notes, that means dew point. And so the air warms, rises, expands, temperature decreases, and if it cools below the dew point, we get condensation, and that spot where it cools beyond the dew point is called the condensation level. So they form at or above the condensation level. That's where clouds form, which is the temperature is at or below the dew point. Alright, and condensation will continue. Latent heat keeps being released and allows clouds to form above that baseline. Below the baseline, the air is still too warm with the latent heat for the clouds to form. Alright, another way of looking at this process called lifting. Alright, if it's not the adiabatic cooling, not the air just kind of rising because it's warm, sometimes air masses have to rise up. If there's a big mountain in the way, air goes up the mountain. And so as moving air rises up a mountain, it will cool and form clouds. Which is why in a lot of pictures you see clouds near the top of a mountain. As that moving cold air moves away, less dense warm air moves upward, alright? And so we create more and more cloud formations. You get mass cloud formations, a lot of clouds forming as more air gets lifted. Because as cool air from the ground gets pushed up the mountain, as the wind blows or something, it pushes the cold air up the mountain. Let me draw a little mountain here. There's a little mountain. So we have cool air gets blown by the wind up the mountain. Well, as that happens, warm air that was already up the mountain, that gets pushed up and creates more and more and more clouds. So you get large clouds as that cool air starts pushing the warm air. So that warm air's got to go somewhere. It doesn't just mix with the cool air, it gets pushed out of the way. Another type of cooling that can happen to the air is called advective cooling. We'll talk about this more when we talk about fog. But that's when warm air moves over a cold surface. Alright, it could be warm air over a lake moving over cold land. Alright, or cold air over land moving over water. And that's what we have, and the reason we have a picture of Golden Gate Bridge here in San Francisco is because it's famous for its fog in San Francisco. And it's because cold air from over San Francisco Bay moves over the city. Sorry, warm air from San Francisco Bay at night moves over the city, which is the ground is colder and causes fog, and then warm air from the city during the day moves over San Francisco Bay during the day, which might end up being a lot colder, and causes fog on the bridges. This is advective cooling, and we mostly see the formation of fog with advective cooling. After we talk about the cloud types, we'll get into more about fog. And that's it for this video. Hopefully, it's a nice little break from that marathon of a 28-minuter from Lecture 1. And we got 2 more left, so you're halfway through the videos of this unit. And by the time you're listening to this, you've had that cloud project described to you, so maybe do a little work on that if you have some time and feel like it. If not, you'll have some classes coming up to work on that. And bring in any questions as always. Have a good night.